Hello, thank you for joining us. Our project is remote sensing of subsurface soil moisture. My name is Beatriz Meadows, and these are my team members.
My name is Toan Nguyen.
My name is Susav, Shrestha.
My name is Easton, Bryan.
My name is Nicolaus, Jennings.
In this presentation, we will share with you the outline of our project, the objective, and the current problem we are trying to solve, what has been done in the past, and our proposed solution to this problem. The current progress that we've made so far, our future work, and the conclusion that we've arrived to. The importance of measuring soil properties comes from the need to prevent and predict natural disasters such as drought, floods, wildfires, and also forecast crop productivity.
Current solutions include wired and battery-powered soil sensors like the RioTemp moisture meter. They use probes that reach up to 1.5 meters deep, but they're hard to scale up for large areas. There's also wireless solutions like NASA's SMAP, which uses radar for passive measuring of backscatter from Earth's surface. This backscatter ends up being dependent on soil moisture. This covers large areas, but only goes about 10 centimeters deep. The proposed solution would combine advantages of both, using radar to detect backscatter from a far-reaching probe as opposed to Earth's surface. The probes are non-invasive and require no power, so that they can be left in the ground for measurement at any time. The proposed system consists of 3 parts: the probe or soil sensor, the interrogator system that gets information from the probe, and the inversion algorithm that processes the information.
The first part of the system is the soil sensor. It consists of an antenna being attached to the probe on the ground. For the design overview, the antenna, after capturing the signal from the radar, will send them down the probe, and some of them will be reflected back. How much they return depends on the surrounding material, which is soil, and the probe physical configuration. So our goal is to find a design that gives a strong correlation between the soil moisture and the reflected signal, which is the S11 parameter. This is our current simulation setup in Tjuatja. We are testing it with stainless steel rod, sandy soil at different spacings, frequency, and a fixed length. We found a good result at 15 millimeter spacings and set up the measurement in the lab. The result from simulation and measurement show a strong correlation at 1.75 GHz, and this will be the antenna design parameters. For the antenna, we picked the multi-antenna and designed it in the Tjuatja, fabricated that, and the results showed that it indeed resonated around 1.75 GHz, which is what we wanted. However, this is not an optimal design, and it had a small gain and a significant backload, which is undesirable. We are working on the new design to minimize that. This is our overall setup for the soil sensor with the antenna and the probe. Next, we're going to be talking about the interrogator system.
The second part of our soil sensing system is the interrogator system. The purpose of the interrogator system is to send out our signal and receive a reflected signal from the soil sensor. This is our block diagram for the interrogator system. This radar system is modeled off the MIT coffee can radar design. This block diagram has been overlaid on our physical implementation. Our signal first starts out from the function generator. This is then passed to the VCO. The output of the VCO is then attenuated, amplified, and split between the transmit antenna and the mixer. The reflected signal is then amplified, sent to the mixer for demodulation, and filtered for signal processing. The transmitter and receiver antenna we are using are Vivaldi antennas. The bandwidth of the Vivaldi antenna is 1.4 GHz, between 1.1 GHz and 2.5 GHz. Our transmit power is 15 dBm from our measurements. In order to validate our radar system, we are observing the range time intensity plot. As you can see, as our teammate approaches the system, the scrolling waterfall of values indicates an object approaching. Then, as she moves away, the range increases as shown.
The final phase of this remote sensing project is to write an inversion algorithm that can take the input from the radar interrogator system and deduce the correct soil moisture. This part of the project is still a work in progress. We plan to develop the inversion algorithm using a machine learning approach. Therefore, we are focusing on obtaining various soil moisture data using our device to create a training model from both simulations and experiments. To bring it all together, our research presents a remote soil sensing system which has deep sensing capability and is ready to take measurements 24/7. This project can be scaled to cover a wide area by placing the probes at different locations. We have built and tested the integrated radar system and the soil sensor. In the future, we'll be collecting soil moisture data using our device for the inversion algorithm. And we will also be optimizing our antenna design. Thank you all for listening to our presentation.